The tip of a wind turbine blade is, it's actually traveling at over 150 miles per hour.
Which is wild to think about.
Right. It's generating just an unbelievable amount of twisting force. But from a distance, they just look like these, I don't know, giant graceful pinwheels peacefully spinning in the breeze.
Yeah, they really do. But if you actually walk up to one and you stand at the base of that massive steel tower, that peaceful illusion completely shatters.
Oh,
You quickly realize you are standing underneath a heavy-duty industrial powerhouse. I mean, the physical scale of these machines is staggering.
yeah, we're talking about hundreds of tons of spinning metal.
Exactly. Pressurized hydraulics, heavy-duty gearboxes, incredibly sophisticated electronics, and it's all just suspended hundreds of feet in the air.
Welcome to the deep dive. I'm so glad you're joining us today because we are taking you on a bottom-to-top mechanical tour of a modern wind turbine.
It's going to be a fun one.
It is. We've got some fantastic source material guiding us today, including detailed technical reports from the Department of Energy, the National Renewable Energy Laboratory, and some industry technical glossaries.
Lots of good data in there.
Right. And our mission today is to just strip away that clean, white exterior and look at the nuts, the bolts, and the grease that actually make these machines function.
Because understanding the underlying mechanics here is deeply practical. This isn't just, abstract physics happening in a laboratory somewhere.
Yeah,
It is heavy industry interacting with the natural world in real time.
and for anyone listening who already knows their way around a diesel engine, or maybe you feel comfortable using power tools, diagnostic computers, or hydraulic wrenches, this topic connects directly to a massive, high-demand career field.
Oh, absolutely.
Maintaining these machines is the job of a wind tech, or wind turbine technician. And it is a highly skilled, incredibly hands-on profession that absolutely does not require a 4-year college degree.
Which is huge.
Yeah. You learn by doing, by wrenching on things, and by understanding how complex systems talk to each other. So today, we're going to break this machine down like we're just on a lunch break talking shop.
Sounds good. And to understand how a machine catches the wind, we first have to figure out how it avoids being pushed over by it.
Right, because that's a lot of force.
A massive amount. The entire system relies on what's happening out of sight, deep underground. We have to start in the dirt.
Let's unpack that foundation,
Yeah.
because I was reading through the engineering specs, and you can't just bolt a 300-foot steel tower to a concrete slab in the grass.
Definitely not.
We are talking about over 1,000 tons of concrete and structural steel rebar, just buried deep in the earth. That is an enormous amount of material just to create a base.
Well, the forces at play require nothing less. I mean, imagine the leverage involved here.
Okay.
You have this towering structure facing brutal thunderstorms, gale force winds, sometimes even hurricane conditions. If you think about, say, holding a heavy broomstick at the very bottom and someone pushes hard against the top of the stick.
Oh man, the twisting force against your hands would be tremendous.
Exactly. That is the kind of leverage the wind exerts on the base of a turbine.
So that underground foundation essentially acts as the anchor to counter all that leverage.
It does. And building it is a major construction event. Excavators dig this massive pit. Crews weave a dense, heavy lattice of steel rebar to give the concrete tensile strength. And then fleets of cement trucks pour continuously so the entire 1,000-ton mass cures as one solid, unbreakable block.
Wow.
Yeah, without that heavy footprint gripping the earth, the wind hitting the top of the tower would just rip the entire apparatus straight out of the soil.
I picture it like the elevator core of a skyscraper.
Yeah.
You don't really see it when you look at the skyline, but it does all the heavy lifting to keep the building completely straight.
That's a great comparison.
And the tower itself is a whole different beast. We're looking at a hollow steel tube standing anywhere from 260 to 350 feet tall. Why do they need to build them quite that high?
It really comes down to the quality of the air.
The quality.
Yeah. If you've ever stood in an open field on a windy day, you might notice the wind at ground level is, well, it's highly turbulent.
No.
It's churning and swirling because it's constantly bouncing off trees, buildings, hills, and the ground itself.
Just hitting everything in its path.
Right. That chaotic air is terrible for generating power. But as you climb higher up into the atmosphere, away from those ground obstructions, the wind becomes significantly stronger, much smoother, and far more consistent.
So you really just have to build the machine up into that fast, smooth air to get the best performance.
Exactly.
And what I find amazing is that this tower isn't just a simple stand. It is a literal daily workplace. wind techs actually have to get to the top to do their jobs.
They do.
They wear these heavy-duty safety harnesses and climb massive vertical ladders attached to the inside walls. Or they use small industrial elevators built right inside this 300-foot steel tube to get to their worksite.
That is a serious daily commute.
I mean, yeah, you really can't be afraid of heights.
It certainly requires a comfort level with heights and enclosed spaces, but once you make that climb up the interior of the tower, you finally reach the components that actually interact with the weather.
The blades. Now, going through the National Renewable Energy Laboratory reports, the sheer size of these blades is just hard to wrap your head around. Like, how big are we actually talking here?
They are colossal. I mean, modern blades are made of advanced fiberglass and composite materials to keep them as light as possible.
Right.
Yet a single blade can easily measure anywhere from 115 to well over 220 feet long.
That's insane.
To put that in perspective, a single 220-foot blade is longer than the entire wingspan of a Boeing 747 commercial airliner.
Wow. And that comparison to an airplane wing is really the key to how this entire machine pulls energy from the sky,
It
right?
really is.
Because here's where it gets really interesting. A turbine blade isn't just a flat board being pushed backward by the wind.
No, it's not.
It doesn't function like the sail on a sailboat catching a breeze.
Right. If it relied on simple pushing, which is a concept in physics known as aerodynamic drag, it would be terribly inefficient.
Okay, so how does it work?
Instead, turbine blades use a principle called lift. If you look at a cross-section of a blade, it's shaped exactly like an airplane wing.
Oh, yeah.
It has a curved surface on one side, and it's relatively flat on the other. As the wind flows over the blade, the air traveling over that curved side actually has to move faster to reach the back edge at the same time as the air moving over the flat side.
Wait, let me try to follow the physics here. Why does faster moving air matter?
This brings in Bernoulli's principle.
Okay.
When a fluid, or in this case a gas like air, speeds up, its pressure drops. The molecules get stretched out, so to speak, so they push down less on the surface of the blade.
Oh, I see.
This creates an area of lower pressure on the curved side, while the slower air on the flat side maintains higher pressure.
And nature hates an imbalance, so the higher pressure wants to move toward the lower pressure.
Exactly. And since the blade is in the way, the higher pressure physically pushes the blade toward the low pressure zone.
The blade is literally pulled forward.
Yes. That pulling force is what we call lift, and it is what violently yanks the blade through the air, causing the entire apparatus to spin with incredible efficiency.
Which is a brilliant design. But, that introduces a pretty serious variable. The wind doesn't always blow at the same speed.
No, it doesn't.
Sometimes it's a light breeze, and sometimes it's a violent storm.
Yeah.
How does the turbine handle those extremes? I read that the blades can actually twist on their own axis.
Yes, that twisting action is called pitch control, and it is absolutely essential for both efficiency and safety.
Okay, how so?
Well, each massive blade is mounted on huge bearings at its base. When the wind is light, the turbine's computer systems tell hydraulic or electric pitch motors to twist the blades to a very specific angle.
You catch more wind.
Exactly, designed to catch the absolute maximum amount of air.
So they angle themselves to grab as much lift as possible. And this happens at what the industry calls the cut-in wind speed.
Right. The cut-in speed is the exact moment the wind is finally blowing just consistently enough, usually around 7 to 9 miles per hour, for the turbine to wake up, pitch its blades, and start generating usable power.
But then, say, a massive storm rolls in. If the wind gets dangerously fast, let's say 55 or 60 miles per hour, generating maximum lift would spin the turbine completely out of control.
Oh, it would be disastrous. It would rip itself apart under the centrifugal force.
Right. So what happens?
To prevent catastrophic failure, the turbine has a programmed cutout wind speed. When sensors detect the wind is too fast, the turbine initiates a protective shutdown. The pitch motors twist the blades completely edge on to the incoming wind. This action is called feathering.
Feathering. I always think of it like sticking your hand out the window of a moving car on the highway.
Oh, yeah, that's a perfect example.
Like if you tilt your hand just a little bit, the wind catches your palm and violently pushes your arm up or down. That's pitch control catching the air to create lift. But if you slice your hand perfectly flat, edge on into the oncoming wind, the air just glides right past your fingers and your arm stays perfectly still. That is feathering.
That is a highly accurate way to visualize it. Feathering allows these massive structures to become basically aerodynamically invisible to the storm, allowing the wind to pass by without exerting any turning force.
So we have these massive lifting blades doing all this aerodynamic work, But they don't just float in the air independently. They all meet in the center to turn that aerodynamic pulling force into mechanical rotation.
Right. The structural center point where all three blades attach is called the hub. And when you combine the hub and the blades together into one single spinning unit, you get what is called the rotor.
So the rotor is the entire rotating assembly facing the wind.
Exactly.
And there's this fascinating physical illusion that happens with the rotor. If you look at a big turbine from a distance, or even stand near the base, the rotor seems to be spinning incredibly slowly.
It does.
Like at the center hub, it might only be completing 10 to 20 rotations per minute. You could almost time a single revolution with a wristwatch.
It looks remarkably slow, almost sluggish.
But it's a total optical illusion. Because the blades are so impossibly long, the tips of those blades are actually traveling in a massive outer circle.
Right.
To cover that huge distance in the exact same amount of time it takes the hub to slowly turn once, the blade tips are flat out screaming through the air at speeds well over 150 miles per hour.
It is basic geometry, yet the physical reality of it is staggering when you think about it.
I picture it like a high school marching band turning a really tight corner on a football field.
Oh, I see where you're going with this.
Yeah, like the person on the inside pivot point is barely taking baby steps,
Yeah.
just slowly marching in place. That is our 10 to 20 rotations per minute at the hub.
Yep.
But to keep the entire line perfectly straight, the poor kid on the far outside edge of the line has to flat out sprint just to keep up.
Working twice as hard.
Exactly. That is our tip speed tearing through the air at 150 miles per hour.
Managing the mechanical stress between that incredibly slow hub and those incredibly fast blade tips requires just brilliant structural engineering.
It really does.
But that slow, powerful rotation at the hub is just raw mechanical energy. We still haven't made any electricity yet.
That's a good point.
That mechanical rotation needs to be converted, which takes us directly behind the rotor into the machine's engine room.
Okay, this brings us to the room sitting at the very top of the tower. In the industry, this is called the nacelle. That is pronounced nacelle. We can think of the nacelle as the boxy housing at the top of the tower, about the size of a school bus. To define it another way, the nacelle is the protective shell that holds all the heavy electricity generating equipment.
It's the nerve center.
Exactly. This is the main workshop. When wind techs climb the tower, this is where they spend their day.
And it is packed wall to wall with heavy machinery. When you step inside the nacelle, the first thing you see directly connected to the rotor is the main shaft. Because the hub is spinning slowly, the main shaft is also spinning slowly, maybe 15 rotations per minute, but it is turning with an unfathomable amount of torque or twisting force.
But you can't just, plug a generator directly into a piece of steel spinning 15 times a minute and expect to power a city grid.
Yeah.
The frequencies wouldn't match at all.
No, the generator requires much, much higher speeds to induce the correct electrical current. So that slow, high-torque main shaft feeds directly into a massive gearbox.
Oh, so it's exactly like a car's transmission, but running in reverse. Like in your truck or your car, the engine spins incredibly fast, and the transmission gears it down so your wheels turn at a manageable speed on the road. But up in the nacelle, the gearbox takes that slow 10 to 20 rotations per minute from the main shaft and uses a series of large gears turning smaller gears to step that speed way up, converting it to over 1,000 rotations per minute.
You're basically trading all that raw torque for high-speed rotation.
Right.
And the high-speed shaft coming out the back of that gearbox is what finally spins the generator. Now, the generator functions largely like a giant version of the alternator in a vehicle.
Scaled up.
Way up, by using the high-speed spinning motion to rapidly rotate massive magnets around complex coils of copper wire. It strips electrons loose and induces a powerful electrical current.
Ah, the fundamental magic of magnets and copper.
Never fails.
And sitting right on that high-speed shaft inside the nacelle is a massive mechanical brake.
That's super important.
Yeah, because if a technician needs to open up the gearbox to replace bearings or change synthetic oil, they need to physically clamp that rotor in place. You don't want a sudden gust of wind accidentally spinning the gears while their hands are inside. It is standard lockout, tag-out safety procedure.
Yeah, a vital safety mechanism for anyone working around heavy moving parts.
And for anyone listening who has wrenched on heavy construction equipment or done preventative maintenance on a diesel engine, this is your world.
Absolutely.
You are using torque wrenches, hydraulic tools, grease guns, and diagnostic computers to keep massive steel bearings lubricated, gears meshing perfectly, and electrical sensors communicating. It just happens to be a heavy-duty engine room suspended 300 feet in the air.
It's an incredible workspace. But a machine that's perfectly tuned is completely useless if the wind changes direction and hits the blades from the side or the back.
Right.
The turbine has to constantly read the weather and steer itself.
Because the wind isn't always blowing straight out of the north. So, sitting on the very roof of the nacelle, exposed to the elements, are a couple of crucial meteorological sensors.
What do we have up there?
First, there's a wind vane, which works just like a traditional weather vane on a barn, spinning to track the exact direction the wind is coming from.
Classic tech.
And next to it is the anemometer, that is pronounced an O-matter.
It is a critical piece of diagnostic equipment.
It really is.
Yeah.
We can define the anemometer simply as a small instrument sitting on top of the nacelle that measures wind speed.
Okay.
To put it another way, it is a tiny spinning sensor that tracks exactly how fast the air is moving to tell the computers when to start up or shut down.
Right. And the data from that anemometer in the wind vane is constantly feeding down into the turbine's central computer. If the wind vane detects that the weather has shifted direction, the computer triggers a heavy-duty steering system called the yaw.
The yaw. Let's define the yaw as the system that rotates the entire nacelle to face the wind.
Got it.
In other words, yaw is the mechanical act of steering the hundreds of tons of machinery left to right so the blades hit the breeze directly head-on.
That's it, exactly.
But I do have a question about the mechanics of this. How does a tiny, lightweight sensor sitting up on the roof physically dictate the movement of a school bus-sized box full of cast iron and copper that weighs hundreds of tons?
Well, that is where the heavy hydraulics and electric motors come into play. Positioned right at the base of the nacelle, where it meets the top of the tower, is a massive ring gear.
A ring gear.
Yeah, it's a giant steel circle with teeth cut into the inside. Engaging with those teeth are several heavy-duty yaw motors.
Oh, I see.
When the wind vane senses a shift in the breeze, the computer sends a signal to activate those yaw motors. They grind their internal gears against that massive stationary ring on the tower, slowly and powerfully pivoting the entire nacelle until the rotor perfectly faces the incoming wind.
Okay, so it is an incredibly smart, highly automated machine. We have perfect aerodynamics with airplane wing blades, high-tech gearboxes stepping up the rotation, and automated yaw motors constantly steering into the breeze.
It's engineering at its finest.
So if we have engineered it this perfectly, how much of the wind's power are we actually capturing? Are we getting like 90% of the energy? 95%?
It's a logical assumption, but this is where the fundamental laws of physics intervene.
Physics ruining the fun again.
Always. There is a hard mathematical limit to how much kinetic energy we can extract from the air, regardless of how perfect the engineering is.
And this brings us to the Betz limit, pronounced B-E-T-Z, named after a German physicist who studied fluid dynamics over a century ago.
Albert Betz. In 1919, he published a mathematical proof demonstrating a very frustrating reality for future engineers.
Yeah, the Betz limit is the physical maximum amount of wind energy any turbine can possibly capture, which tops out at exactly 59.3%.
Right.
Stated another way, the Betz limit is an absolute ceiling on efficiency for pulling kinetic energy out of moving air.
It's a hard stop.
I have to admit, the first time I was reviewing this in the Department of Energy Sources,
Yeah.
I had to stop and think about it.
Yeah.
Yeah, like, why only 59.3%? Why can't we engineer a futuristic, hyper-efficient composite blade that captures 80% or even 100% of the wind's energy?
Consider what it would physically mean to capture 100% of the kinetic energy from a gust of wind. Kinetic energy is just the energy of motion.
Right, the energy of the wind moving.
If the turbine blades extracted absolutely all of the motion out of the incoming wind, the air would have to come to a complete dead stop the instant it hit the blades.
It would just freeze in midair.
Exactly.
Yeah.
And if the air stops moving entirely, it doesn't go anywhere. It just sits there, hovering directly behind the rotor.
Oh, wow.
It would instantly pile up, creating a massive invisible traffic jam of stationary air. And because that stagnant air is blocking the path, no new wind could physically get through the rotor.
The turbine would essentially plug up its own airflow. It would block the wind from hitting itself.
Precisely. For the entire system to function, the air has to retain a certain amount of speed just to get out of its own way.
It has to move.
Right. It has to exit the back of the turbine to make room for the next gust of wind coming in from the front. Betz mathematically proved that the absolute perfect balance, extracting the maximum possible amount of energy while still leaving just enough speed in the air so it can clear out of the way, is 59.3%.
So even a theoretically flawless machine built with perfect alien technology maxes out at a B- in efficiency just because of how fluid dynamics work.
Pretty much.
That is an incredible constraint to design around.
And modern commercial turbines operate surprisingly close to that theoretical limit. The precision of the pitch control and the aerodynamics of the blades really push the boundaries of what physics allows.
Man, stepping back and looking at the entire picture we've painted today, the scale is just phenomenal.
It really is.
We started deep underground, looking at how a 1,000-ton concrete and rebar foundation uses sheer mass to fight the leverage of a storm.
Yep, the unseen hero.
We climbed up a 300-foot steel tower, bypassing the turbulent ground air to find the smooth wind. We broke down how airplane-style blades use the low pressure of Bernoulli's principle to generate lift, twisting on their pitch bearings to catch the breeze, or feathering out to survive a gale.
And we examine the physical geometry of the rotor, where a slow, high-torque hub drives blade tips moving at 150 miles per hour.
Incredible.
And we went inside the nacelle, watching the gearbox trade that torque for the high-speed rotation required by the generator to strip electrons and push power to the grid.
All while the anemometer and the yaw motors constantly hunt for the perfect angle in the breeze. It truly is a marvel of heavy industry, mechanics, and aerodynamics all working in concert.
Definitely.
But I want to leave you with one final thought to mull over, building right off that Betz limit we just explored.
Okay, let's hear it.
If a turbine is extracting nearly 60% of the energy out of the wind, the air coming out the back of the machine is drastically different from the smooth, fast air going in.
Oh, yeah.
It has been robbed of its energy, it is slower, it is churned up, and it is highly chaotic. This turbulent exhaust air is called the wake.
You can visualize it just like the choppy, swirling wake left behind a fast-moving speedboat on a calm lake.
So imagine you're a project manager tasked with building a massive wind farm featuring dozens, maybe hundreds of turbines.
That's a big job.
Right. If you arrange them incorrectly, the second row of turbines is going to be suffocating on the slow, turbulent wake created by the first row. The wind will be ruined before it even reaches them.
That would be a very expensive mistake.
Huge! How do you stagger them? How many rotor diameters apart do they need to be spaced to let the wind recover? It is a massive, multi-million-dollar puzzle for structural engineers, and it all comes back to the simple physics of how air moves.
It is a complex challenge, demonstrating that scaling up this technology requires just as much precision as building the machine itself.
It is endless problem solving. Now, today was entirely focused on the standard horizontal propeller design. That three-blade shape is what most of us picture when we hear the term wind turbine.
The classic look.
Exactly. But next time, we are exploring wind capture technologies that look absolutely nothing like the ones we talked about today.
We will be diving into the mechanics of vertical axis wind turbines.
The unconventional designs. We will be looking at things like the Savonius, that is pronounced Su-V-O-H-Nius, and the Darius, pronounced Darius. These vertical turbines don't look like airplane propellers at all. They look like giant egg beaters or massive S-shaped scoops spinning on a pole.
They're fascinating to look at.
And they pull energy from the wind in a totally different way without ever needing a yaw system to steer them.
So if you enjoy visualizing how things work and have mind for mechanics, join us next time as we tear down a totally different kind of engine.
See you then.